All right, so once again, reminder for your final exam next Wednesday, 10:30 a.m. in the Elliott Hall of Music. Make sure you get there a little bit early. They'll let you into the building at, I think, around 10 o'clock. You can stay in the lobby and just wait it out. But once you get into the hall itself, look for where you're supposed to sit. If you get lost, look for TA or look for me. All right? Okay, so we're going to continue doing a few of the problems that we didn't get to. I want to start with number 9 on 2014. This is on a trig substitution, a rather tricky one, so we should look at it. We did quite a bit of series and stuff last 2 times. Let's look at a few integration problems. So here we're trying to calculate integral from 1 to 3 x squared plus 2x minus 3 under a radical. Okay, and you've learned quite a bit of different integration techniques. It's always a question as what you should do. The clue here, I see a radical here. That's always a pretty good clue that trig substitution is a good way to go. Not always the case. Sometimes we can get away with using a substitution. But in this example here, a trig substitution is a better way to do it. Okay? So if you see a radical, think about trig substitution being an option. But to use trig substitution, we need a radical of sum or the difference of squares. Right? That's the other requirement to use trig substitution. But we don't have that here. This is not a sum or difference of 2 things squared. But we can make it squared, that form here, by completing the square under the radical. Right? So let's get it out of here and just work with it for the moment. So first we look at these 2 terms, x squared plus 2x. There's a minus 3 here. We'll leave it out for now. Come back to it. Completing the square, remember we take 1/2 of the coefficient of x and then square that. Right? We take 1/2 of this term, square, added to here. But if I added something here, I got to balance that by taking the same thing away. Okay? So I added this to complete a square, and then I take it away, so I don't change the quantity. And now we got x squared plus 2x plus 1. That's a perfect square. X plus 1, the quantity squared. And then 4 here, that's 2 squared. And even if that's not a nice number like 4, we can still deal with that. But we need to have difference of squares or sum of squares before we can do our trig substitution. Okay? So this is what we're integrating here. Next, we do a trig substitution. Remember, you want to make a triangle. With sides given by the expression here. The first one is the square root of the first term under the radical. The second one is the square root of the second term under the radical. And the last one is the way it is. Exactly the same thing. All right? Okay. Actually, I need more room, so we'll do a triangle on the new slide here. Here's my triangle. You always want to start with the hypotenuse. So which one of these three should be the hypotenuse and why? But not square, though. X plus 1. Yeah, he's right. We're going to take x plus 1 as the hypotenuse. Because looking at the radical expression, it's a difference. So you pick the one that shows up first. It's going to be bigger than the other one. Therefore, it's going to be the biggest side of the triangle. So we chose this to go to hypotenuse. Next, which one should go to the adjacent and why? So we got 2 or this radical thing. I want to put one of them on the adjacent side. Which one should I pick and why? Not 4, 2, right? Why 2? Yeah, it's a constant. Remember, if you can choose where the constant goes, always pick the constant, put the constant on the adjacent. Then the last one, you have no choice but to take the remainder like that, right? Okay? Okay, next thing you do is to try to relate x to theta in the simplest way possible. So we use the 2 simpler sides to do that. Looks like a cosine is a good choice here. Here we related x to theta by using secant. So we have x is equal to 2 secant theta minus 1. And the radical I'm trying to integrate, but the integration I'm trying to do, let me bring it back here. Okay, so that's the problem we're trying to solve. We need to account for dx. Since we know what x is, we can get dx by differentiating that. And what's the derivative of secant? No. Secant tangent. All right. So if you didn't know that, that's something you need to know. What's the derivative of tangent? Secant squared. Good. Okay, so we can replace that. Now let's replace the stuff under the radical. X plus 1 squared, looking at this expression here, is 4 secant squared. Factor the 4 out from under the radical. We have 4 times secant squared minus 1. And what's secant squared minus 1? Tangent. Yep. Those are the identities you have to be able to use. Taking the radical, this is 2 tangent. Okay, so now we can replace that. We can replace that. And very important part here is to also replace the integration limits. The limits refer to x. So we're going to go to a new variable, theta. So 1 and 3 need to be changed so they reflect what theta should be. You can look at any of these expressions. Let me look at the first one here. We see that theta is inverse cosine of 2 over x plus 1. First, the upper limit. If I plug in 3 into the inverse cosine equation here, I get theta as inverse cosine of 2 over 4. And what's the inverse cosine of 1/2? Pi over 3. Good. Then we repeat that with x is equal to 1. And what's the inverse cosine of 1? 0. Excellent. Okay, so new integration limits are 0 to pi over 3, right? Okay, now we can finally integrate this thing. All right, so 1 to 3 turns into 0 to pi over 3. This radical expression we saw really turned into 2 tangent theta. And then dx is 2 secant tangent. And in this problem, you don't have to integrate the whole thing. They wanted to come up with an expression that has theta and new limits in it. So this is all we have to do here. All right, so that's all we need to do. Okay? All right, so a pretty difficult problem, lots of steps involved. Questions? No? Okay, so you know what you need to do with trig substitution. You need your basic identities, right? Without the basic identities, this problem is pretty hopeless. Okay, so we're done with that. Let's look at what's next here. Let's do another integration here. This is number 7 from 2014. One to e, x squared natural log of x dx. And this one we have to do integration by parts. That means we need to pick one part of the stuff we're trying to integrate, call that thing u, and the other part, call that dv. You remember the order in which we have to choose. We should choose u. Right? Log first, inverse, trig, algebraic, trig, exponential. It's hard to write vertically. But there we go. So that's the order we choose our u, right? Log first, inverse trig next, algebraic, trig, exponential. Here I'm seeing an algebraic versus a logarithmic. So I'm going to take log first to be our u. Anything else you didn't choose, they go to dv. Next, we differentiate u and integrate dv. All right, then it's uv minus the integral v du. And I'm going to integrate this first, and then I'll come back and deal with integration limits. uv minus the integral of v du. And now I'll deal with the integration limits. Right? Okay, now we're subbing e here, 1/3 e cubed natural log of e minus 1/9 e cubed minus 1/3 natural log of 1 minus 1/9. And this is a 0. So we end up getting, what do we get? And that's a 1, right? So 1/3 e cubed minus 1/9 e cubed plus 1/9. Simplify more. Let's see, this is 3/9 minus 1/9 is 2/9 plus 1/9. There we go. So that's the answer. Okay, that's pretty easy if you know how to integrate by parts. Yeah. Where? Oh, here. Oh, because that's screwed up. What else is new? Okay, sorry. Yeah, I should be more careful. My fault. Other questions about this one? Okay. All right, I want to look at a few more integration ones. And then we should look at vectors for a little bit. This is number 11 from 14 again. All right, so looking at this here, notice that this is an improper integral. Because 1 over radical 4 minus x squared does not exist at x is equal to 2, the upper limit here. And that makes this an improper integral. Therefore, the first thing we do is to get that 2 away from the integration. Putting a new symbol called that a, and then we'll integrate that as is, and then eventually take a limit allowing a to go to 2 from the left side of 2. And here we see radical and a difference of squares. That's another trig substitution problem. And the three sides we get are 2x and radical 4 minus x squared. The first thing here, square rooted. The second thing here, square rooted. And then the radical as is. And this one's like the one we did earlier. This is a difference. So the leading one, square rooted, becomes your hypotenuse. Then you got 2 remaining here. Always pick the one that has a constant to go to the adjacent. And then the x has no place to go except hypotenuse. Then relate x and theta in the simplest way possible using the 2 simpler sides. We're going to do a sine, opposite hypotenuse. Then we get dx. Don't forget dx. The most common mistake I see is people will do all of these substitutions wonderfully and then forget to take care of dx. Don't forget dx. Okay, so that's what we got. And then we also need to take care of the limits, right? Here, theta is the inverse sine of x over 2. So when x is equal to a, theta is the inverse sine of a over 2. And we'll deal with that when we integrate. And then when x is 0, theta is inverse sine of 0. That we know is at 0. Okay? And then one last piece to substitute. This stuff down here, 4 minus x squared. So that's a 4, 1 minus sine squared. And this is a 2 cosine. Right? That's a cosine squared. So when I take the square root, I get 2 cosine, because 4 comes out of the root and becomes a 2. Okay, now we finish the integration. Right. All right, 0 to a becomes 0 to inverse sine of a over 2. And then this stuff, dx, is 2 cosine. And then radical 4 minus x squared is 2 cosine. That's actually pretty nice. Right, 2 cosine will cancel, so we get a d theta left. Then the integration is trivial. When you integrate d theta, you get theta. And we eventually get this thing. And now we let a go to 2. In fact, we can let a be exactly equal to 2. Sine doesn't care when a is 2, right? This thing had a problem with x being 2, but here we can let a be 2. No problem. 2 over 2. And inverse sine of 1, we all know that, is pi over 2, right? So there we go. All right, questions? Good? Good. Okay, let's do a couple of things with vectors. Let's just do a quick review of vectors in general before we do problems. All right, so if I have 2 vectors, yeah. Yeah. Yes, always the same. So let me bring that problem back here. So what I like to do is just handle this part first, clean that up, and then bring the whole limits back, even evaluate the whole thing. But if you wanted to, you could have evaluated earlier and then finish that integral. But often sometimes there are ways to simplify before you do that. It's not a big deal. It's just a personal preference. But to answer your question, yes, you use exactly the same limits. Okay, do you remember the definition of the dot product? What's A dot B? Magnitude of A, magnitude of B, and cosine theta, right? And remember, theta is the angle between the 2 vectors. Stop. What about the cross product? The magnitude of the cross product. Who remembers this? It looks kind of like that. Yeah, what do you think? Yeah. And geometrically, what is A cross B? The magnitude of A cross B. Very good. Okay, if you do A cross B and then take the magnitude, you get the area of this thing. Couple more things that might show up on the exam. The vector projection, written as component of B onto A, of B onto A. Who remembers what the formula is? Good. This might show up on the exam, so probably you should find out. No, wait, this is the scalar, sorry. No wonder everyone's confused. Scalar projection. There we go, perfect. Now the vector projection of B onto A. Do you know the formula? Good. Sometimes you see it written this way. Right? This part is the scalar projection. And what's this thing here? A over magnitude of A. It's a unit vector. Good. Unit vector in the direction of A. All right, so these are some basic stuff we ought to know. You ought to know. All righty, now let's do a few problems. Let's do number 2 from 2014. That's a good one. Find the area of a triangle with vertices at 1, 0, 0, 3, 1, 1, and 4, 1, 2. Right? So what's going on here? We got 3 points. I'll call them P, Q, and R just so we can refer them to as something. Right, so we got 3 points floating in space. So here's the triangle we're talking about. So what you can do here is to use the parallelogram idea we just saw. Let's come up with a vector that goes from P to Q. Call that A. And then a vector from P to R, call that B. And we know from earlier that if I cross them and find the magnitude, I get the parallelogram. If I just want a triangle, then I divide it by 2, right? Okay, so let's find out the vector A. How would you write a vector A that goes from P to Q? How do you find it? Right, so we're going to do 3 minus 1, that's a 2. 1 minus 0, and then 1 minus 0. Right? So this is P to Q. So you take the destination coordinates, subtracting away the origin coordinates. And that's 2, 1, 1. And then similarly for B, its destination is R, origin is P. So we take destination coordinates, subtracting the origin coordinates, 3, 1, 2. Okay, let's do the cross product. When you want to do A cross B, you take A, put them in the second row, and then B in the third row. Remember how to do this? Yes? No? Maybe? Yeah, what do you think? Right. Yeah. So for the first one here, we cover up the I column and the first top row here. Right? And then we multiply this. 2 times 1 minus 1 times 1. That's a 2. 2 minus 1. Remember that? Yes? Something you should know by next Wednesday. Okay, what about the J? What's tricky about the J part? Yeah, we got to change the sign. Look at that. All right, J. So 4 minus 3, positive 1, but I have to change the sign to negative 1. And then K, negative 2 minus 3. I'm sorry, positive 2 minus 3, that's a negative 1. Now, where did that red pen go? Here it is. Yes. It's 4. It is. Yeah, it's 1. What am I doing? It's 4 minus... Anyway, it's 1. Thank you. So what's the magnitude? How do you find the magnitude? One squared plus minus 1 squared plus minus 1 squared. whole thing under a radical. That's radical 3, right? That gives me the parallelogram, but I want the triangle. So I got to divide this by 2 to get the area. Okay? All right. Questions on this? Okay, be sure you know how to find the scalar projection, vector projection, how to find triangle area or parallelogram area, how to do cross product, how to do dot product. All right, now we got 10 minutes left. Any request on what kind of problem you want me to go over? Something I haven't covered but you want me to look at? Yeah. A series expansion of anything particular you have in mind from either of these two exams?
I've got one on the spring one that I just didn't know where to start.
16 spring 2010, you said? 2015, number 16. Yeah, we could do that, but that's not a series expansion one. Did we do number 19 from spring? That's a series expansion one. We didn't do number. Why don't we do number 19 and then 16? 19 is the series expansion. So, and then we'll do 16, number 16. We want the first 3 terms of the Maclaurin series of that. So you have to know the definition, right? The definition doesn't mean we're going to use it, but it's something you have to know. That's the definition of Maclaurin series. Now you got to make a decision whether you want to differentiate this enough times to form the Maclaurin series, or use an existing Maclaurin series to come up with a new series. For this one, you just want the first 3. So if you want to differentiate it, you can up to second derivative. That's not too horrible for that expression here. So either one is okay for this problem, because we don't want a whole lot of terms. But it's still, you can see it's easier to do it this way, right? So first, we're going to do this part by reusing that. Okay? And then I want an x. That means I multiply x to my existing Maclaurin series. I just want 3 terms, so I'll write it out. N is equal to 0, that's a 1. N is equal to 1 gives me negative x squared. And then n is equal to 2 gives me positive x to the 4th. So x minus x cubed plus x to the fifth. But again, it's not terribly hard to differentiate this twice. Now, if we didn't say do the 3 terms, we want the general summation notation, now that would be a difficult task. Okay, is that what you had in mind, kind of? Okay. Questions on this? So this one you have to know. We're not going to give you this one. But things like sine, cosine, e, inverse tangent, natural log, that's it. Those things we will give them to you. Okay? But we are not going to give you the definition. You have to know the definition. All right, let's do number 16. It's not a series expansion, but it's actually a geometric series problem. It's a little bit tricky. So what you want to do here is to split this up into 2 series. Right? And then rewrite these things a little bit. The second one is easy to rewrite. Let's do that first. So that's clearly a geometric series with a common ratio of -2/3, right? The first one will do something very similar. Two to the n minus 1 can be written as 2 to the n over 2. So the first expression can be turned into that. It's 1/2 2 to the n over 3 to the n, or 1/2 2 over 3, the whole thing, to the nth power. Two geometric series, we know the formula to find the sum, right? The first term in the series is 1/2 times 2 over 3 over 1 minus the common ratio. Repeat that for the second one. The first term in that series, when n is 1, over 1 minus the common ratio. Yeah. No, we're forced to start at 1. But, you know, the formula doesn't care where you start. It cares about the first term and then the common ratio. So if you can identify the first and the common ratio, it doesn't matter where we start. We could start at 18, and it doesn't change the way we find sum. Okay? So first term over 1 minus ratio, right? So that's the way to find sums. What does it turn out to be? This is 1/3 over 1/3. That's a 1 plus minus 2/3 over, what is that? 5/3? Sure. So that's 1 minus 2 over 5. And that's a 3 over 5. Okay? And with that, we are out of time. When's the exam? What time is it? Where is it? Okay, good luck with your finals. See you on Wednesday.